Hello, good afternoon, everyone. Welcome back to another week of learning large language models. And today we're going to focus and do more deep dives into large language models, as well as a topic inside of it called reinforcement learning. So let's get started. So, as an introduction, large language models, as we know already, are sophisticated AI models that can generate text, translate languages, write different kinds of creative content, and answer questions in a really informative and creative way. So we're going to unravel the magic behind these models and focus on how they were built and the crucial role of reinforcement learning in their development. So when you're building an LLM, what are the stages? Well, the first stage is pre-training. And this is the foundational stage where the model is trained on a massive data set of text and code. And the goal is to create a base model that can predict the next token in a sequence given the previous tokens, as we talked about previously. This is essentially teaching the model the statistical patterns of language, hence the large language model. And in our process, we have to do some data collection from the internet. We have to tokenize text into tokens using algorithms like byte pair encoding, otherwise as known as subword tokenization. Model architecture, so utilize a neural network architecture, a transformer model to deal with sequential data, and training to predict the next token in a sequence given the context of the previous tokens, which can be done by adjusting the model parameters. And as an outcome, you'll see that a base model that has learned the statistical patterns of language and can generate coherent text. So this is like your GPT-3, GPT-4, but it's not yet fine-tuned for specific tasks or aligned with human values. There is something you can do with LLMs called fine-tuning. In short, it just means that you get rid of that pre-training phase and essentially train it on a very specific data set um, and have it be really good at that statistical pattern. Now, let's talk about post-training. So this is basically the stage where the base model is fine-tuned and aligned to perform specific tasks and exhibit desired behaviors. So we have something called SFT, supervised fine-tuning. And essentially the goal is to adapt that base model to specific tasks and make it follow instructions, such as I could fine-tune a model on writing very simple Python code. So maybe it'll be fine-tuned on different ways to generate a calculator app. So every time I prompt it to tell me to write a calculator app, it's really good at it. Um, Now, obviously, to do this, you have to do a lot of data collection to provide where humans provide instructions and tell the model what the output should be. And fine-tuning essentially is continue training the base model on the new dataset and adjusting the parameters to align its behavior with the human demonstrations. And so, as again an outcome, you get a model that can follow instructions and perform specific tasks. However, it can still generate harmful or biased outputs. All right, now let's actually talk about reinforcement learning. So, the goal of reinforcement learning is to further align the model's behavior with human values and preferences and to improve its ability to reason and solve complex problems. So, there's actually quite a funny way. I think the first time I saw reinforcement learning was someone teaching a game AI to jump over a gap in a 3D environment. And essentially, that was just a lot of reinforcement learning that eventually led the AI to learn how to jump over gaps. And they did this by incorporating a reward model where it's essentially trained to predict human preferences for different model outputs and RL fine tuning, which is just using reinforcement learning, where it receives rewards based on the reward model's predictions. This encourages the model to generate outputs that are aligned with human preferences. So, again, back to that example where the AI was jumping over that gap in the game, the human would tell the model that they were getting closer and closer. So the closer they got, the bigger the reward they were gonna get. So that is a level of reinforcement learning. And as an outcome, you'll get a model that is more aligned with human values and can reason better and is less likely to generate harmful or biased outputs. Now, types of reinforcement learning. We have reward modeling, where human labelers provide rankings of model outputs. The reward model is trained to predict these rankings. We also have proximal policy optimization, where essentially the model is fine tuned to generate output that maximizes the reward predicted by the reward model. And so there are some challenges and criticisms here. For example, reward hacking, where the model may learn to exploit the reward model to get high rewards without actually generating good outputs. And scalability, where the reinforcement learning can be extremely computationally expensive and time consuming, as it requires human values and inputs for the model to continuously get better. Now, there are some really clear benefits, such as reinforcement learning helps align the model's behavior with human values and improve the ability to reason and solve these complex problems. So maybe the time invested and computation, processing, all that is worth it. You can kind of see this with some of the newer models we see, like DeepSeek, where they were used unsupervised reinforcement learning to essentially make their model really good at reasoning. So, how LLMs learn to follow instructions. So, instruction tuning is the primary method for teaching LLMs to follow instructions, and we can look over the process. First, human labelers provide examples of ideal responses to a wide range of prompts and instructions. They're essentially emphasizing helpfulness, truthfulness, and harmlessness, and it's fine-tuned on this data set to learn to imitate the desired behavior, which basically allows it to follow instructions and generate responses that are aligned with human expectations. And you know, doing all this will make it so that it will act more human, maybe talk a little bit more like humans do, so it's easier to accept by a wider audience. But how LLMs actually develop themselves? Well, the thing is, they don't have a persistent sense of self or identity, and the responses to questions about identity are based on patterns in the training data and specific context of the conversation. Developers can use system messages to provide the model with a sense of identity. For example, I could give a system message to a model saying, "You are a helpful desk assistant at a hotel." And now that model associates itself as a hotel desk manager. Um, and some conversations can be hard coded into a model's response to the questions of themselves, and we see that with DeepSeek and anything with China mentioned. Um, all right, let's go on to hallucinations. So LLMs can actually sometimes generate outputs that are just straight up wrong or nonsensical. These are called hallucinations. Now, there are some ways to mitigate this. For example, you can train the model to say, "I don't know," when it's uncertain. You can tell it to use external tools to find more information or verify its information. And you can also give it fact checking mechanisms to verify its outputs against reliable sources. Now, the importance of reasoning. There are a couple ways to implement reasoning. Number one is chain of thought prompting. This basically encourages the model to generate a series of intermediate reasoning steps before arriving at a final answer. This can obviously improve the model's reasoning ability and reduce hallucinations. And of course, reinforcement learning can be used to improve the model's reasoning ability by rewarding it for generating coherent and logical chains of thought. And this is what we see with DeepSeek and why they were so good at it. Now, what are some limitations? Well, we can kind of think of it as a Swiss cheese model, where they have strengths and weaknesses. Their performance can depend on the task and the context and what it was trained on. Multimodality is very tough to handle for different inputs and giving different outputs. LLMs can be used to create intelligent agents to perform complex tasks, and as if in the future, and for test time training, where researchers are exploring ways to let LLMs learn and adapt during inference, which can lead to more efficient and personalized models. So, all in all, what have we learned? LLMs are powerful tools that have revolutionized many aspects of our lives, as we know by now. And by understanding how they are built and the role of reinforcement learning in their development, we can better appreciate their capabilities and limitations, work towards creating even more advanced and beneficial AI systems in the future, and hopefully create the AGI. Or I don't know, maybe that's the point, right? All right. Thanks for watching this week's lecture. I will see you next week. Bye bye.